Alrighty, so this is the last section that's on exam 2. Duke is here now. Come here. You want to say hi? Come say hi. Up, all the way up. Okay. So 2.7, we're still talking about linear models. So, but specifically now we're talking about where lines meet. So not in the last section, but we kind of could have made that connection. But we've talked before about like where lines meet and specifically also where they don't meet. So we said that we can find the intersection by two equations by setting them equal to each other. And we talked about, we did a problem for it was something like this in y equaled 500, which is like something right there. And that point right there is the intersection of the two. So when we say like we want the output to equal that amount, that's kind of what we're talking about, right? So if they're lines, this will look like y equals 1m or m1x plus b1 intersects y equal to m2x plus b2 at the same x value, right? So if they're intersecting, they have that same point x, y. So the y's are going to equal, and so it'll be m1x plus b1 equaling m2x plus b2. So with the x values, that satisfies that equation. That's what we're looking for, right? So it poses the question sometimes when solving for these x values is how many times is this point, are these like two lines going to intersect? Duke? Knocking over cups. I was worried about them, right? So we've heard of lines intersecting one time, right? When we have two different lines. So let's draw our little axes, and then I'll make copy. Okay. Right, so we can have any arbitrary line and a second line. And they're going to intersect right there. So two lines will intersect once. If they are two distinct lines, two distinct lines. And by distinct, we mean nothing in common, right? We've also seen when they will never intersect, so 0 times. So bring out my little axis again. There we go. So one goes like this, and the other one goes like that. And they keep going off forever. So two lines with same slope and different y-intercepts, right? But what if their y-intercepts are the same? How many times will they intersect then? Think about that as the same line. So two lines, oopsies, made that a little thicker than I wanted to. So two lines with same slope and y-intercept. That's pretty much the same line, right? So every point that they share, every single point on that line, they're going to have, and they're going to intersect at those points. So we would say an infinite amount of times. So 0, 1, or always, right? So that's the case where parallel lines, if they have the same y-intercept, they're the same line, but I can call one, I think we've had examples where it's like a pumpkin or a witch is called a line. And we can write lines many different ways. So I'm like, when does this equation and this equation intersect? Do they happen to be the same? They intersect an infinite amount of times. All right, so those are your options. So let's find the point of intersection between G, F, and G, where F is 5x minus 8 and G is 3x plus 2. So the point, that means I want an x, y, all right? So, okay, make sure you can see. So basically, we want to set 5x minus 8 equal to 3x plus 2. They're going to share that point. So since these are both technically y equals, or my output equals, I can just set them equal to each other. So I'm going to add 8 and subtract 3x. So I'll get 2x equals 10 and x equals 5. Well, that's just the x value, right? I'm not done yet. I need in my xy point. I want a point, not which x value. No, I don't care. I do care, but I just want to find the point. How do I find the y? Well, we just need to plug into one of these equations. Does it matter? No, because we set them equal to each other. So no matter which one I plug in, f of 5 should equal f of, or g of 5. If it doesn't, we did something wrong. So in the beginning of practicing these, it might be good to test both of them just to make sure. So I do 5 times 5 minus 8. So 25 minus 8, 20 minus 3, so 17. What about g of 5? Let's just to check. We'll do 3 times 5 plus 2 equals 17 as well. Perfect. So they both match. So my answer would be not 2. I don't know why I said 2. 5, 17. Great. So that's a good way to check yourself, is to see if when I plug it into the other function, I get the same output. All right, and then I need to write it as a point because that is what I'm asked. All right, so I love this problem. We had a whole conversation about this problem one time in class because it's really interesting. And if you're in the market to buy a car, like I am, it's also very useful. So Kevin needs to buy a new car. He compares the cost of owning 2 cars he likes. Car A is 18,000, gas powered, and gets 20 miles to the gallon. Car B is 25,000, but it's hybrid electric. So it gets 48 miles to the gallon. For this comparison, he assumes that the price of gas is $4.50 per gallon. Let's assume he lives in California somewhere. I don't know. I actually remember it being pretty high when I was in high school, somewhere in the 3s. Yeah. Maybe the 4. I don't know. Find a linear equation that models the cost of purchasing car A driving X miles. Okay, so this has a lot of unit conversion in it. Okay, so we learned last time to make these linear models, one is to see what my variable is, but I'm already told that X is miles. So now I need to take all the numbers and information I have and put them into expressions and then put them into the model. Right, so purchasing car A, let's call that A of X, is going to be the cost of the car plus the amount of money we're going to send per mile. and then times X, because that's the number of miles, right? Per mile. So I know the cost of the car from A is 18,000. What about cost for driving X miles? So we get 20 miles per gallon. So I get 20 miles for every 1 gallon. But then I also get $4.50 per gallon. So I want money per mile. So actually, I think we want to want money on. So I want $4.50 for every gallon. And then I'm going to flip this so that it is 1 gallon every 20 miles. It's the same. And then gallons cross out. And we're left with 4.5 divided by 20. $0.225 per mile. Perfect. All right. That's kind of the unit conversion that I learned in my physics class that has been really useful when doing these things. Because units, you can also just think about them as part of the number, like the thing that gets canceled out. So why percentages don't have units. That's the unit. And I want money over mile. Okay, so A of X. Now I'm going to put everything together. So 18,000 plus 0.225 times X. Alrighty. Great. Now let's do it for B. So we're going to copy and paste this because it's going to be pretty much the same, just the numbers are changing. All right. So instead of A of X, we're going to call this B of X. Oh, there we go. The cost of that car is, oh, this should be another 0. What is it? 25,000? Perfect. Gas is still 450, but now I'm going to get 48 miles per gallon. So that's going to change. 4.5 divided by 48. Oopsies. 0.9375. And it's only those 4 decimals places. So, oops, I just made a big mistake. There's a 0 right there. It's only those guys. So I'm just going to keep all of them just because it'll make my answer a little bit more accurate. All right. So that means that B of X will equal 25,000 plus 0.09375 times X. Okay. So find the break-even point for Kevin's cost comparison. That is, find the number of miles he needs to drive so that the cost of owning car A is the same costing and owning car B, right? So B has a larger intercept but a smaller slope. A slope closer to 0 is going to be more flat versus a bigger slope or more negative one is going to be more steep. So if we're just drawing like a rough comparison of what's going to happen, first we know that the slopes are different and the y-intercepts are different. So it's only going to intersect at one point. So probably what's happening is like the hybrid car is kind of going up like that really slowly. And then the other one's like down here and its slope's like twice as much. And it's going to go something like that. Right. So there's a break-even point where they're going to be the same at first. The cheaper car is going to be more affordable. And then the hybrid over the long run is going to be is better for your bank account. Right. So we do the 18 plus 0.225x equals 25, 0, 0.09375 x. Okay, let's subtract 18,000. And then we'll subtract 0.09375 x minus the 2. 18,000. Okay, so those go away. Okay. 0.225 minus 0.09375. So this is 0.13125 x equals 7,000. So x would equal 0.13125. There we go. Must mess that up. Whew, okay. 53,330. Wait, it's going to keep going. 33333. We'll just call it 3, right? So find the number of miles he needs to drive, right? X is miles, so this would be miles. Great. And that is the distance that he would need to drive to then make the hybrid vehicle the same amount as the gas-powered vehicle. Okay? Pretty cool. You should look up like a Tesla. Actually, no, that isn't the same because you don't buy gas for that. I'm thinking about buying a RAV4 hybrid. So look up that, the cost, and like the local gas station near you. And then whatever your car is now, if you have a car, and do that price evaluation and see what you get. That's a fun thing. We spent like a whole class period doing it, and it's actually really fun and interesting. So there's something useful. Buy a car. So if you buy an expensive car, make sure that you're driving it long enough to make it worth it rather than buying a cheaper car. Okay. So this is a fun one. Petra and Jordana go on a bike ride from their home to the beach. Petra was slow getting ready. So she left 5 minutes later than Jordana. Jordana was like, later, the UV is 10. I need to get my tan on. Jordana did not care about Petra, which is really sad. Okay. On this trip, Jordana rides at the average speed of 5 meters per second. And Petra is 8 meters per second. She's trying to catch up. So let t equals 0 be the time when Jordana leaves home. Find a linear equation that models Jordana's distance in y from home at time t. Okay? So at time t, where is Jordana? So let t0 be when Jordana leaves home. So she's just taking the step outside the front door, but she's still at home. She's just leaving, right? For like a millisecond, she's at home. So Jordana has the 0.00. So it's y equals, what's her speed? Average speed is 5. So her slope is 5. So 5x plus 0, or just, oh, not x, sorry. Don't know what x is defined as, only t. So y equals 5t. Okay? So find the linear model that Petra's distance. So Petra doesn't leave home until 5 minutes later. So there's a few things that we need to be careful of. Our things are in meters per second. So time is in second, right? So if I put 1 in here, so y equals 5, 1, that's saying 1 second. She'll be 5 meters away, not 1 minute. So we need to be careful. Your slope tells you output over input units, right? Meters and time in seconds, okay? So 5 minutes t equals 5 times 60. Also not very good at my sixes. There we go, 300, that's what I thought. Equals 300, okay? So Petra has the point, if we're thinking about on a graph, at time 300, she's finally leaving the house. So if I draw like a quick little graph, so for Jordana, she just like left, right? And she kept going. Petra didn't leave for the beach until like 300 seconds later, and then she left, right? But we're just kind of want to model this linear model, but it really would look like this, even though she's not going any farther away. But that's if we just continued our linear thing. So, and we know her slope is, what? 8? Okay, yeah, 8 meters per second. So, we can do point slope. So we do like y minus, minus 0 equaled 8 t minus 300, or y equals 8t minus, whatever this big number is, 2400. Let me make sure that's right. Okay, good. Alrighty. So even though obviously she's not ever that far away from home, that's just, we're modeling it, right? So like this line would keep going down and down and down and like finally intersect the y axis there, but we know that she actually doesn't, but this just models when she leaves, okay? Kind of just adjusting for her starting so late. So how long does it take Petra to catch up to Jordana, and how far have they cycled away? So how long does it take? So time, and how far? Why? The distance. So we're gonna have 5t equal to 8t minus 2400. Let's subtract 8t. So we have minus 3t equals negative 2400 divided by, I think it's gonna be 800. I just want to make sure. Yep. So t is going to equal 800 seconds. And if you wanted to, you could answer in minutes. Divided by 60 seconds per minute, which is going to give me 13.33 minutes. All right. So both of those are correct. They're just, if you want to know minute wise, and then how far away they were, plug into one of them. Probably plug in the one that's easier to calculate. 5t versus 8t minus 2400, just do 5t. So y equals 5 times 800, which I think is going to be 4,000, but I'm not sure. My mental math is not great lately. 4,000, there we go. And that is meters. So they cycled, they did a 4K just to catch up. All right. Beautiful. All right, cool. So with these linear models, we can also apply it to business stuff. So like supply and demand. So economists model supply and demand for a commodity using linear functions. So for example, for a certain commodity, we might have our supply be y equals 3.82 p P, so that's the price, the change, because we can change the price of a commodity, minus 10.51. A commodity is just like something that you can pay for, right? Often confused with your health, because your health is not a commodity. How much would you pay to feel better? Pretty much a lot. Anyways, so supply, if the price goes up, then this is the supply, right? Hold on. Yeah, supply is the increasing one. And then demand would be something like Y equals negative 0.99 P plus 25.34. There we go. And Y is like the number that we're selling, right? So if my price goes up, this is a negative slope. So I'm going down. My demand goes down. People are like, oh, I don't know if I really want it for that much, like, but it's so cheap earlier, blah, blah, blah. And then if when price is increasing, you would also expect the supply to increase and stuff like that, right? So I have a definition and I don't know what that definition is. Oh yeah. I think it's the equilibrium. Actually, we're gonna pause and see if I can figure it out. Oh no. Hold on. Okay, I'm back. It was the equilibrium point. I just don't want to tell you guys the wrong thing. Okay, so the equilibrium point is the point of intersection of the graphs of the supply and demand, right? So, what can we say about the product produced? Oh, it's the product produced. If I increase the price, I'm also going to increase the number I'm making so I can make more profit. That's supply. Okay. So if I draw a beautiful little graph, supply is our increasing one, right? So there's supply. Here is demand. These colors are a little too close. Let's do a different color. Let's do this purple. Right, this decreasing one, right? So this is demand and supply. So when supply is greater than demand, no one really like wants, right? Like it's like too many. We have too much. That would be called a surplus. If the demand is really high and the supply is low, so in between it, right? If we're under that supply line, it means we have that supply. This is what we would call a, oh God, what is the word? Surplus. Like a drought. Oh my God. I'm annoyed. Surplus. Y'all are probably like screaming at me right now. I'm gonna put comma drought because I can't think of it. Like a scarce, there's not enough. All right. But this equilibrium point is I'm making just as much as I want, right? Shortage. Oh my God, okay. Thank you. Been doing crosswords a lot, so I have lots of words running through my little head. Okay, what can we say about the amount of product produced at this point? So, at the equilibrium point, the amount of supply equals the amount demanded. So there is neither, that's not how you spell that word, a surplus or a shortage, right? Which is good for foods like, or commodities like food. Some companies like that shortage. Keeps the drive going. Anywho's. All right, so some guy models the market for wheat by the following equations. They're the same equations we just talked about a little while ago. Here pieces the price per bushel in dollars, and Y is the number of bushels produced. Yes, okay, and sold. So I made them and then I sold them. Use the model for supply to determine the point where the price is so low that no wheat is produced, right? Like it's not even worth the farmers making it. It costs so low, right? That's why if you saw my little supply thing didn't actually ever intersect, right? You would think like, oh, 0, and they won't make anything. But there's a price, right? You need a little something to get you moving forward. All right, cool. So no wheat produced, right? Y is the number of bushels produced. That's the supply, and sold, that's demand. So this would imply that Y equals 0, right? So if we draw this, right? I want to find when Y equals this dude and Y equals 0 intersect. I know we said, oh, we just plug them in. I mean, we do, but so, oh wait, that wasn't my color 4. There it is. So it'd be like something like this intersects with this line right here. Okay, I want to find that point. So right there. So 0 equals 3.82p minus 10.51. So we're basically, I mean, you're like, oh, didn't we just plug in for Y equals? Yes, but Y equals 0 is the line too, right? Same with X equals 0. It's also a line, just that other way. Okay, cool. So 10.51 equals 382p. Wee, 3.82. And the price, the farmers are going to be like, I can't sell it for that little. I cannot feed my family. 3.82. There we go. Is 275. What in dollars? In dollars. So $2.70 is the cheapest they can go without losing money, pretty much. Or they would probably, that's the point where they would be making money right after that. Okay. If they sold for that price, they wouldn't really be making any money. So making no wheat would be better for them. All right. So use the model for demand to determine at what point the price is so high, no wheat is sold. So again, this is when Y equals 0. And I wonder if I can grab this up here. Copy. Paste. And it was like this purple line. Okay. Has anyone been listening to that song about Jeff Bezos that Bo Burnham wrote? 'Cause it's kind of been stuck in my head. Zuckerberg and Buffett. It's been stuck in my head. So this y equals line right here is going to intersect your demand all the way out of here. It's so high that people are like, you know what? I'm going to go on a low carb diet. Not going to buy any more wheat. All right. So y equals, what is our demand equation? Negative 0.99. You guys should eat carbs though. They are good for you. 25.34. Okay. And that's going to equal 0. 0.099 p equals 25.34. So let's do this. 0.99 p equals 25.34. So p will equal, what, 27? 25, no, not even close. Good job. $25.60. Smack a dollar sign on the front. So when the price is that high, no one wants to buy it. They're like, ooh, the products are really expensive. They'll forego that commodity because it's too expensive. Okay, cool. To find the equilibrium price, the quantities produced and sold, and the quantities produced and sold at that equilibrium. So now we're going to smush these two guys together. So let me grab my demand equation, copy, paste. Copy, paste. Right, so these two things are now both equal to some y, right? I want to find that commodity. So we're finding quantity. So I want to find the price, which is x, and the quantity, which is y. So again, I want that point. I don't care about y equals 0. Okay, so we're going to add 0.99p plus 1051. And that's going to give us 481p equal to 58.53. So p is going to equal 35.85 divided by 4.81. So 7.45 dollarinis. Okay, so that's where enough people are like, I'm gonna buy myself a loaf of bread. That wheat is a good price. And on the other hand, the farmers are like, yeah, enough of farmers will make that same amount. So it's perfect. No food waste. No one's hungry. Win-win situation. Alrighty. Oh my God, we're done. I didn't know we were. I thought we had more problems to do. Okay, so this is the end for exam 2. So Wednesday's material, if you're watching at the same time, will be not on exam 2. So 3-1, 3-2. So remember that 1.4 was on exam 1. So it won't necessarily be covered, but I still could ask you, is this a function? Why? You are allowed graphing calculators on this next one, but I don't think you'll need them. Anyways, that's about the exam. I'll send you a big email. Don't need to tell you here. All right. So I'll see you guys tomorrow.